you're going to be working with a lot of different components. And those components typically have a voltage that you run those components at. And that's because as you increase voltage, you increase current. Current and voltage are linked proportionally. So more voltage, more current. Less voltage, less current. And the point of voltage is because you can control the voltage directly. You can't control the current directly in the same way. So basically, circuits are designed to work with an amount of current, and using some math, um, electrical engineers calculate how much voltage needs to be applied to get that current, because then we can take voltage and multiply it times current to get wattage, and then that's the total amount of power. Um, but what is current? So current is the flow of the water. Basically, like um, electricity in these electrical circuits are made of these little electrons that travel through the wire. And basically, you can think of it like water molecules. And current is the flow of those actual water molecules, or in this case, electrons, as they move through the circuit. So if you just have a very small current, then you have a very small flow of electrons. If you have a big current, you have a big flow of electrons. And there's two types of current, alternating current and direct current. So in the walls, we use this thing called alternating current. And basically, the water is moving back and forth, or the electrons are moving back and forth 50 times a second, or 60 times a second. I'm not sure what it is in India. Um, and then direct current is just flowing in one direction. So if you have a battery, that's going to be doing basically direct current. Um, so using current and using voltage, you can calculate the amount of wattage or how much electricity your thing is using. 60, yeah. So those are the two most important things to know about electricity before you can start designing circuits.
Okay, and remember, if you guys have any questions, you can put in the chat or just unmute and ask us, and we'll be happy to answer to the best of our ability. Okay, so one of probably the most, not most, but one of the most important concepts to know when making electrical circuits or learning about electrical engineering in general is something called resistance. So resistance is the measure of how difficult it is for an electrical current to, can flow through a material. So again, let's use this example that they've listed here. So imagine a narrow pipe. The flow of water through that would be much slower compared to a pipe that was larger in radius. So things like ohms, right? So ohms is the unit of measure for resistance, and that describes how much resistance the flow of electricity faces. So if you guys remember back to our Arduino unit, our microcontrollers unit, I showed you guys some Arduino boards, right? Like I showed you the Tinkercad, and you guys messed around with that as well. One of the things in the top of it when you were adjusting and playing around with it is you could change the number of ohms when you added a resistor. So a resistor again is what causes resistance, and ohms is the unit by which we measure resistance. So in that Arduino example, we could literally change the amount of ohms, like we could increase it or decrease it to change the resistance of energy or the flow of energy that was passing through. So again, an ohm is measured by voltage divided by amperes. So voltage V and amperes I, we talked about those previously. And then an example of this would be 1000 volts divided by 25 amperes, which is equal to just 40 ohms. And things to think about like this, right? When you're making much larger circuits where you have much more energy flowing through, you'll also need much more resistance, right? Or maybe less resistance depending on what you're making. But there's also different versions. So like kilo ohms or deca ohms, all of these exist, just like the metric system. So that's something to keep in mind.
Yeah, so the way we calculate ohms is using this formula. So a lot of electrical circuits is just formulas. These are very basic formulas based on physics. If you take a level two physics course, you typically discuss a lot of these formulas. And you can actually build these equations from the very basic foundations of physics. But this formula is one of the most important formulas in all of electrical engineering. It is known as Ohm's law. And this is how we calculate um, the resistance. So voltage is equal to the current times the resistance. So if you remember, we can set the voltage And then from the voltage, we have to design our circuit so we have a certain amount of current. So for instance, a typical 9-volt battery, well, this is going to pop out. Yeah, that popped out. So here we have a typical 9-volt battery. Um, and using a typical 9-volt battery, basically we need to figure out how much resistance we have to apply, how much resistance needs to be in the circuit to get the correct amount of current. And then we can use the current times the voltage to calculate the power. So this is one of the most important equations. So we have uh, the equation listed three different ways in the top bottom right corner. So voltage equals current times resistance. Current equals voltage over resistance, or resistance equals voltage divided by current. And all three of these equations are equivalent. Using any of two of our components, we can find the third one using Ohm's law. This is how we design circuits. So it's a very, very important law. Along with power equals voltage times current is another important one. And if you combine the two together, you get one of the best equations. And that is power, so your wattage, is equal to your current squared times your resistance, which can once again be derived from this formula. So it's a good formula.
Okay, so here are a picture of some of the electrical components that we talked about and that we will continue to talk about. So the first one that we have here is resistors, right? So resistors, we talked about it being measured in ohms and it basically just limiting the amount of energy that is being passed through. So if you see these colored bands throughout this resistor, there's four over here. So these basically represent how much ohms it has. So there's different resistors with different amount of ohms depending on what you need. Here we have capacitors, inductors, variable resistors, transistors, and diodes, all of which we will talk about later. So these are just kind of an images of what those look like.
And if you're wondering, this is a small FM circuit board. These are some of the same components on an actual circuit. It's kind of hard to see, but same components.
Okay.
So, what are resistors? So we talked about this a little bit when we were discussing Ohm's law, but pretty much the entire point of a resistor is to have resistance. Basically constrict the pipe or oppose the flow of electricity. If we didn't have resistors and we applied some voltage across a circuit with zero resistance, we would have infinite current, which technically is impossible. Um, but if we had infinite current, the battery would explode and we'd have a lot of issues, which is not great. So basically, resistors, the entire point of a resistor is to cause the voltage to drop, constricting the current and turn some of that energy into heat. Um, and there's a lot of different types of resistors. And the bottom right, we have symbols, and we're going to get into diagrams in a bit. But the most common resistor is a fixed resistor in a diagram. And that's what you saw on the previous page and also right here. That is a fixed resistor. It's just that little tan-looking tube with a bunch of stripes on it. And you can read those stripes using a very simple online diagram. Um, and basically, a resistor has a fixed set of ohms plus a tolerance, which is not very important. Um, yeah, of course, Thomas. Um, and basically, by using resistors, we can constrict the current and make sure that we don't draw too much current for a circuit. These other types of resistors are also very useful. So a variable resistor is also known as a potentiometer. And if you see this little knob here that turns, this is a variable resistor. And the way it works is we have a bunch of little things on the back. And as we increase the potentiometer, and it's turning on the radio. As we increase the potentiometer by turning it, this variable resistor, we can actually adjust the resistance. We don't have to add multiple resistors. We use one resistor, and as we turn it, we can change the resistance between some range. Another very interesting type of resistor is a photoresistor. This type of resistor increases its resistance to light. Actually, I think it's the other way around. When you apply a light, it becomes less resistant. They probably make both types. And this is useful. So if you've ever seen those like street lights that turn on at night, or one of those little garden lamps that turn on by itself at night, that is a photoresistor. All it's doing is sensing when the light gets dark enough that it needs to turn on. the circuit senses that the resistance is lowered, so it turns on the light. And then these other types are not as important. Adjustable, tapped, and thermistor. I mean, they're very important. But there's just more types of resistors that you can use. And a thermistor is a very common one. If you ever have a pot or kettle that boils water, basically what that has is a little thermistor in it. And as the temperature increases, the resistance also changes. And once it hits a certain limit, the circuit knows, okay, there's so much resistance, we need to stop the circuit, cut it, it's hot enough. So resistors are incredibly important, and without them, we cannot do anything in electrical engineering.
Okay, so what are capacitors? Capacitors store electrical energy in the form of an electrostatic field, electric fields that are not that don't change over time. So that's what an electrostatic field is, and release it when needed. So it's essentially something that just holds it or stores electrical energy until it's needed. So there's two types of capacitors. First one being ceramic. A ceramic capacitor is a fixed value where the ceramic material acts as a dielectric or a insulating material. The second one we have here is electrolytic, I'm not pronounce that,
Electrolytic.
electrolytic, and it has a higher capacitance value amount, which is the amount of electrical charge a capacitor can hold, but lower voltage values. And over here are some of the symbols. Hopefully, Michael can explain that a little bit.
Yeah.
Yeah.
Um, there's just a lot of different types of capacitors out there. The general type of capacitor, important ones are the non-polarized capacitors. So those would be your ceramic capacitors, and I think I have one right up here. So if you look in this top right corner, it's kind of hard to see, but all those little kind of like caps that look like circles, those are ceramic capacitors, and they don't have a polarity. That means you can plug them in backwards, just like resistors. You can mix it to plus and minus; they work the same. And that would be the symbol for polarized capacitors, the blue one. The one of the little plus symbol in the corner, that is known as a polarized capacitor, and that's the electrolytic capacitor. It'd be the one that's these type with the little caps on top. These do have a polarity. If you plug them in backwards, they will explode. Um, and a lot of smoke and fire. And also, if you overcharge them, you put too much voltage across them, it will also explode. Um, but basically, like Suhan explained, all capacitors do is they hold a charge. So they're like little batteries, except they don't provide a continuous charge, they provide a static charge. So it's like the equivalent of if you rub your hair with a balloon and you have that static charge. That is exactly what a capacitor is doing. It is taking some of those charges and storing them on one side, so there is a voltage across the two. But as soon as you connect the voltage, it will discharge the capacitor. It's a little more complicated to explain how they are used. Um, but when you chain a bunch of capacitors together in certain shapes, they're invaluable to creating electrical circuits. A lot of your voltage regulation circuits, you have to have capacitors. Power supplies, capacitors. Everything uses capacitors. It's the second most important component next to resistors, arguably. But they're very different component, but they're very important.
Yeah, so diodes, right? This is another component that is also important. So diodes allow for the flow of electricity in one direction, but not the other. So as you guys may know, if we have a power source and then we have something like an LED, is this example, or something else, we only want electricity flowing one way. We don't want electricity going back this other way because that wouldn't work, right? The circuit wouldn't function. So this is what a diode does. Again, there's two types of diodes. The first one is a rectifier, and the second one is an LED. The rectifier turns the alternate current direction back into the direct current. The LED or light emitting diode emits light when electricity flows through it, showing that the path is working. So LEDs, right? Lights that we have like in your room, I'm sure, or you've seen like LED strips. All those are again the same thing, light emitting diodes. So it just basically shows when current is passing through, hence why they're usually all strung together. Um, that picture I'm not familiar with, Michael.
Oh yeah. It's just more diagrams. So,
Yeah.
like Suhan said, diodes they're pretty simple. They just allow electricity to go in one direction and not the other. So you know how AC current, we were talking about the stuff in your wall goes back and forth. If you ran it through a diode, the diode's only going to capture when it goes forward. So it's going to be like a I forget what you call that type of wave. Um, but basically, instead of going back and forth, it's just going to move forward just in a very jagged motion as you apply through a diode. And when you apply a bunch of diodes and capacitors together, you get a rectifier, which is how you turn alternate current back into direct current. And once again, these are just a bunch of different diodes. If you're interested, you can look into the specifics. Obviously, you should know what an LED is because this is one of the most more used diodes. But diodes are used just for their electrical properties, but LEDs specifically are able to produce light. So they're commonly used in a lot of different appliances, including just light fixtures or Christmas lights and stuff like that.
Okay, so what are transistors? Transistors amplify electricity by taking a small input signal and drawing from another power supply to create more energy output. So there's two types of these transistors. The first one is called NPN, and the first one is called PNP. So they're very similar. You just need to make sure to differentiate between the two. So NPN, the first one, energy flows from the base, which is the battery, to the emitter, which would be the output, when powered by a current. The second one, PNP, is when energy flows from the emitter to the base. So basically the other way around. So they're just flipped version of each other. And in the diagram, you can see where the energy is flowing through this arrow. The E being the emitter, the B being the base, and it just basically passing through. It just shows that flow of current.
Yeah. Just a quick note. So transistors are a little different from all the other types of components. Mainly because once you start dealing with transistors, you're dealing with what's called digital components. You of course can use transistors for analog components, but one of the biggest uses of transistors is digital because basically the transistor powers everything about technology today. Every phone, every computer, every device is just billions of these small little transistors packed together in a tiny space. ICs or more complex circuits are all built of transistors. These are actually, I would say, this is the most important component of electrical circuits, other than resistors and capacitors. Um, it's used in almost everything, but yeah, I just want to mention that.
Okay, so an introduction to circuit diagrams. So circuit diagrams are a basic drawing of what a circuit is going to look like. All of the components in the past slides would be incorporated into the drawing to represent what is happening in the diagram. So everything that we just learned about, transistors, resistors, capacitors, all of those will be used over here, and they each of them have different symbols. So let's see one that I've heard before. So G and D. We learned about GND during our Arduino unit, when I showed you guys what all the different wires do, where they go in. So does anybody recognize what GND stands for or what it means?
Ground.
Ground. Perfect job, Thomas. So that's the grounding cable. And then we'll talk about all the rest of these later. But yeah, good job, Thomas.
Yeah. So it's gonna start talking a little bit about logic gates. Um, so now that you've looked over some of the basic tools, you basically have everything you need to make a circuit. That's pretty much all there is to it. Circuits are just these couple bit different components. Once you form a diagram, then you just have to design it into a circuit, solder it together, and you have a working circuit. You're basically there. But now we're going to talk a little bit about logic gates. Um, and this gets into the digital side of circuits. So there are two types of circuit signals, analog and digital. An analog signal would be like if you imagine a wave. So if you've ever seen a audio file and you see that sound wave as it's going up and down, or if you ever play a vinyl record, I know that might be kind of a dated reference. Um, or any other type of analog device, basically the signal itself contains information in the voltage value. So as the voltage increases, that's trying to say something. So for instance, I'm talking right now, and if I was talking to something that was analog and I was trying to store as an analog signal, um, as I talk louder, basically the microphone has a resistor in it that senses the vibrations produced by the sound I make, and it would store it as a voltage signal between 0 and like 8 or 0 and 5. And as I talk more, the voltage signal goes up and down, up and down. So that is analog. But in today's society and most technology today, we use what is known as digital. And what digital basically means is everything is stored as a zero or a one. And this is why we use transistors, because transistors are great for this. They can take input signals where one means it's on and zero means it's off, and combined in the correct way, you can actually process or compute data to get what you want. And that's where logic gates come in. And basically, what these logic gates are, these basic eight logic gates, is are that they are combinations of transistors in such a way that we get certain behaviors from our inputs. And these are the eight different logic gates. So each of these logic gates are going to take one or two input signals and process them in some pattern to produce an output signal. But each of these signals can only be of two states, on or off. There is no in between. Um, so we're going to talk a little bit about the eight different gates here. I think there are actually more. What you can do is invert these gates, I think, and you get more gates. But anyways, these are the eight basic logic gates. So for instance, the AND gate is the first one. And a lot of this actually follows with computer programming as we were talking about previously. So if you remember those if statements we were using, if this and this happen, then let the thing inside the if statement occur. That's exactly what the and logic gate does. It basically says if signal one and signal two are on, then output a signal to signal three. But if signal one or signal two are off, then you're not going to output a signal. Um, the OR gate is exactly what it sounds like. If A or B is on, then output a signal. The NOR gate says that. Oh, okay, the wrong one. The NOR gate basically says that both signals, either signal needs to be off to output a signal. So if A or B is not on, it will output a signal. So it's the opposite of the AND gate. And I'm not going to go down the whole list because you can just look this up. But these are the basic logic gate symbols, and these are all the different logic gates. And what you can do once you understand a logic gate is you can combine them. So you make this thing called a bus. And a bus is basically a set of zeros and ones that you make your input. So for instance, if you have one logic gate, it would have a size 2 bus because you only have two inputs. But if you're able to combine, like, let's say 16 of these logic gates in a certain pattern, you can make this thing called an 8-bit bus. Um, and basically what that means is you enter in a string of zeros and ones that is 8 bits long, and it will spit out some output that you designed it to do. And it's very easy actually to develop these circuits. And one of the easiest applications of this would be to make like a calculator. You would just make a bus and you would enter in two 8-bit numbers. I'm not going to get into binary, but binary basically is like base 10, except it's base 2, and you can translate between the two. So you can convert the number 24, or you can convert some keys on your keyboard into these binary sequences and process it using logic gates. Currently, we use 64-bit technology, meaning our bus is 64 bits wide. So as you can imagine, we use billions of logic gates in current CPUs today, packing together in small processors that we can fit in the average cell phone. Incredibly important tool. Good to know.
Definitely. Okay, so here are some common symbols used in circuit diagrams, which we have a basically a list right down here. Oops. So let's look through these. I'm not going to go through every single one of them, but just the main ones over here. So over here at the top right, we have resistor. So resistors, which we talked about earlier, variable resistors, transformers, all of these go under that. And again, this is when we're drawing out that circuit diagram. This is where we're using resistors. Pretty straightforward. We talked about diodes over here. This is how you draw a diode. Voltmeter and like potentiometer, what Michael was talking about earlier. If we want to have a variable resistance or variable resistance, we would use a potentiometer. Um, Over here on the very left side, we have different types of lights and switches. And then we have our connected and not connected at the very bottom. If you look all the way at the right side, we have some very basic ones, which of course you'll need to know. wires, right? So when you saw that square diagram that we saw earlier, there was those. What was the line connecting them? Well, that was a wire. Then we have the cell, the actual battery itself, the switch to turn it on and off to break that current. Because I mean, we don't want that current to go continuously, right? Or maybe you do, but typically speaking, you don't want that current to go forever. So that's what the switch is for. Then we have our bulb and our buzzer.
Mhm. Yeah. So let's do a quick circuit diagram example. So this is a very, very basic circuit, which only consists of three components connected by wire. But basically, what we want you to do is identify what are these three different components. So we're going to call whatever that thing on the left is A, the thing on the bottom B, and the thing on the right side C. So in chat, if you just put down A, B, and C, and what you think each of those are.
So I can say the answer.
Yes, go ahead.
Mhm.
I think I know only the A and B one. A stands for battery and the B stands for switch on and off.
Yep.
Correct.
And someone actually put C in chat. Dipesh or Dipesh?
Yes, the page.
Uh,
So he said
Dipesh.
LED. So that is correct. So C would be an LED. If we go back into our slideshow here, one second. If we go, oh, there it is. Yeah, so here's the answers for that. So here it says the 5 + 5 volts represents the battery. Thomas was correct. B represents the switch, which is also correct, and then C represents the LED light. So all of those were correct. So good job, guys. So an extra challenge would be, what would happen if this switch is closed? What will happen to the circuit? Anyone
Electricity
can.
will flow in that circuit and LED will light up.
Brilliant, exactly, right? Because the switch is being turned, and that wire will now connect, so that energy will flow in that circuit, and thus the diode will turn on. Very well done. So this is another example. Let me take all this off really quickly. Yeah, so this is another example right here. So try and see if you can label what each of those are. We'll give you a few seconds for that if you want to put into chat or if you want to unmute and
5
tell us.
volts is the battery,
Yep,
4.7 kilo ohms, and the other one, they both are resistors, and the last one uh might be also a resistor.
I think it is, yeah. Yeah,
yeah,
that's correct.
yes. And what does kiloohms, what does that measure?
The amount of resistance that the resistors are putting on the flow of electricity.
Brilliant. Well done. Everyone get that? Okay, well done. Perfect job.
We have one more example. This one's a little harder.
And this is the answers for that. So, okay, now we have a real challenge. I'm going to give everyone 2 minutes, and at the end of that 2 minutes, I want you to type in chat what each of them are, and I'll label these very
And
quickly.
also, extra challenge, if any of you can tell us what the circuit will do, um, what the circuit's supposed to do.
Yeah, the purpose of the circuit.
It might be a little hard to see because it is a more complex one.
The purpose of the circuit is to light that LED which is there with the power of 1 volt, 3 batteries, and there are 2 resistors and 1 diode which are allowing the electricity to flow towards the LED. And also, I don't know what is Q1, 2, and 3904.
Yeah, so basically what you said was good. I don't think there's a resistor, but basically what's happening here is we want to power the resistor, which requires a voltage of 9 volts. The power of the resistor, and we only want it to happen when we hit those two switch buttons, SW1 and SW2, which you identified as switches correctly. However, we don't want to run 9 volts through our switches um, because for some reason 9 volts through the switches would be an issue. And there's a lot more electrical knowledge behind that on why you don't want to run high voltages through your switches, like you could get electrocuted. So instead, we want to run 1 volt through our switches. But 1 volt is not enough to power the LED. If we put a 1 volt charge, and you click that button, and connected it directly to the LED, which is labeled D3, um, then the LED will not turn on because the LED has this thing called a threshold, which is the minimum amount of power it needs to turn on. And in this case, we're just saying that the LED will require 9 volts. Now, in reality, LEDs don't typically take more than 5 volts, so it'd probably be closer to 4. But that's not important for this. But basically, the way that this circuit works is we're actually using a transistor and a logic gate. Um, so when we click SW1 and SW2, the 1 volt signal, um, both 1 volt signals go to the AND gate, and the AND gate takes an on or an off. So 1 volt means it's on, 0 volts means it's off. You don't want to put 9 volts through your transistor because then your AND gate at the top because then it'll explode. Maybe not with 9 volts, but it's definitely going to get very hot. Um, but basically, when you click down your two switches, both A and B, your paths, are given 1 volt. And the AND gate says if A and B are both 1 volt, if both buttons are pressed, then output a signal of 1 volt out of the top. So then that 1 volt signal comes out the top and it goes to the transistor, Q1. And 2N3904 just refers to the exact specification. So each of your components, you can look up they have a code number associated with them, and if you look it up, you can just find them across the internet where you can buy these components. And these just happen to be 29, 2, and 3904 just happens to be a type of transistor. But basically, the 1 volt signal is fed into the transistor, and because the transistor detects the 1 volt signal and it has a 9 volt power behind it, it says, okay, it's going to activate. So then it feeds a 9 volt power through the transistor, which gives it enough juice to power the LED. So it's a little more complicated um, than the previous circuit. So instead of just clicking a button, we end up having its own logic circuit, which in turn powers the actual circuit using a transistor.
Exactly,
So,
and Dipesh listed it out very well. He listed all of those very well, so I wanted to recognize him for that. He also has a question. So he says, "In which item are these circuits used?" So I'm considering, I'm guessing you're talking about all circuits. So we talked about earlier circuits being used in practically well, literally every electrical component, right? So big things like laptops, TVs, mobile phones, those have more complex electrical circuits. But even things like our light in our room, those are electrical circuits, right? Really simple things like anything solar powered, that also is an electrical circuit. So really anything that is controlled by electricity that you can see, that all uses a circuit. Hope that answers your question for that one. Okay, and here is our answer for this one. So you can see what it says over here. Battery 1 and 2 power a weak signal, and both buttons need to be pressed to activate battery 3 over here. So battery 3, that's why it is part of a separate little function over here, and that amplifies, the LED. Okay.
yeah. So I can talk a little bit about circuit analysis because this is a little more complicated outside the scope of what we're going to talk about.
Yeah,
So I'll just
so
skim it.
quick thing I'd like to add. And so again, what we're going to go through on the next few slides is a little bit more higher level, just like Michael was saying over here. So I just try and stay with us, pay attention, and we'll get through it.
Yeah, of course. If you have any questions, make sure to shout them out or put them in the chat. But don't worry if you don't understand this. This is definitely more advanced than what you probably will be working with in most basic circuits. But basically, when we have circuits and you're designing circuits, we use two analysis tools, and these are called nodal analysis and mesh analysis.
What do we mean by nodal and mesh analysis?
That's a good question, and that's exactly what we're going to get into in the next two slides. Oh, it's not on the next two slides. I guess it's all on this slide. Um, Basically, these are the two tools we use to calculate um, the amount of voltage, current, and resistance of our different components. So basically, if you remember Ohm's law and power equals I squared R, and all of our other electrical circuit um, equations from earlier, we can apply them using these two methods called nodal analysis and mesh analysis to calculate what resistances we need to get the required currents that we want. Um, so nodal analysis uses this thing called Kirchhoff's current law, and basically this says the sum of all currents entering and leaving a node must be zero. So hence the name nodal analysis. And basically the idea is to look at the currents. So in that little circuit on the bottom left, we have two batteries, 3 volt and 2 volt. Both of them are pumping current up and towards that center point VA. And basically, what nodal analysis says is all the current, all the water, all the electrons flowing into that point VA from the left and right must be equal to the amount flowing out of I3, the one way out. So basically, you can set up your equation and show that the amount of current flowing in through those two paths in must be equal to the one path out. And that gives you a very basic current equation. And then what you can do is combine this with Kirchhoff's voltage law in this thing called loop analysis or mesh analysis. And what this says is you take some point on the circuit and you take any path on that circuit in a full loop and come back to that point, the total voltage must be equal to zero. Um, because any voltage you gain is then lost. As you pass through a resistor, there's this thing called a voltage drop. And your voltage basically goes from whatever you set it to and drops down to a lower level. Um, Obviously, this is a little hard to explain, but basically, long story short, you have these two very amazing tools, and when you combine them, you can calculate all the voltages, currents that you need when designing these circuits, understanding them, and doing full circuit analysis.
Absolutely. Okay, so a series circuit. So series circuit is when there's only one flow of electricity in the entire circuit. So this is unique because we can create some formulas with it intuitively. So to find the total voltage, we can just create a series where we add the voltage at each point to get the total voltage. So V1 and V2, which is voltage 1 and voltage 2, and that can go on forever, is equal to the total voltage, which is V total. So total resistance will always be calculated in the same way, in the same formula over here. And then here we have a diagram at the bottom. So we have a battery at the very bottom. We have a positive and negative side, which is charging, or which is powering each of these diodes or LEDs over here.
Hello, sir.
Yes, Thomas, go ahead.
Sir, the circuits used in a house, they are parallel circuits, right?
Yep, parallel.
Parallel.
Because you don't want to be using a series circuit in a house because
If if one goes off, the other one goes off with it, doesn't it?
exactly.
Yes.
Each
So
component drops the voltage.
so if you guys have seen, I'm not sure how common this is in India, but Christmas lights, right? So a few years ago, I remember at least we had a string of LED lights that we would put on our house for Christmas or Diwali. And it was one of these. It was a series circuit. So basically, if one little LED goes out, or if one LED breaks, or if the current to one goes out, then the entire LED thing has to be replaced because all of them will go out. So we figured out that that was a series circuit. Nowadays, you'll see people selling more of parallel circuits. So if one breaks, you can replace it, and the entire thing doesn't have to be replaced or break. Yeah, good observation, Thomas.
Oh, yeah. So parallel circuit, as Thomas mentioned, is the other type of circuit. And basically, when you wire your circuit together, each component is connected independently from all the other components. So instead of adding the voltages together, you add the reciprocal of the resistances together. And this just boils down to the math of it. Um, so you're probably wondering, why would you do this? Well, the most important reason we would do this, is the voltage across the entire circuit is the same. When you wire a bunch of different components in parallel circuits, each component is given the same voltage. So adding more components to your parallel circuit doesn't actually affect the voltage of the circuit. You still have the same voltage for each of your circuits. This is why we use parallel in houses. If I plug my toaster in, I don't want it to drain all my power away so my refrigerator doesn't work. I want to be able to run all my different components at once without each, each individual component messing anything up. And then the second important thing, as Suhan and Thomas mentioned, is if one component fails, the entire thing is taken offline. Or if you want to add a component to the chain, you have to turn off the circuit first. Parallel circuits, um, changing out a component of the circuit, unplugging it, or having it fail doesn't affect any other of the components on that circuit because they're not connected together in series. They're in parallel. So we commonly use parallel circuits, but series circuits are also important, especially for batteries, as you want to stack the voltages together.
Yeah. Okay, so we're nearing the end of it right now. So here's one of the last topics that we'll cover, and that is combination circuits. So these are the circuits that have both series and parallel circuits. So just like I talked about series and Michael talked about parallel circuits, they're a configuration of both. So as you can imagine, they're very complex. For these ones, we would analyze the parallel circuits first, then add the simplified resistance of the parallel circuits to the series circuits, and then use Ohm's law, which Michael talked about earlier, to figure out any other math needed. So what this combination circuit is, it's basically adding a bunch of things that we learned before, right? So we see things like Ohm's law, we see parallel circuits, we see series circuits. So it's just a combination of all of these. And in this last sentence, it talks about the order in which we would kind of analyze this. So again, we would analyze the parallel circuits first, simplified resistance of the parallel circuits to the series circuit, and then use Ohm's law. And here's a diagram at the very bottom. So we have input A and input B. I'm going into this. And then we have our output via cell B. And then we have cell A, and we have this LED over here. So yeah, that's a little diagram of a combination circuit.
Excuse me, sir.
Yes, go ahead.
So, what is the meaning of quorum sensing processor?
Of quorum sensing repressor. I'm actually not sure.
That's a good question. I'm gonna be honest.
Let
Let's
me.
see.
That's a
Quorum
good.
sensing are proteins that bind to autoinducers. This is for bacteria. I have no clue what it's doing in a circuit diagram.
Oh, wait,
It
so
probably is important for something, but I do not know.
hold on.
Plus receptor, repressor. Yeah, this is a protein.
Yeah, it's talking about biology. Huh.
Huh. I actually have no clue. That's a good question.
Yeah, that's a very good question. We will look into that. That's a good thing you brought up, Thomas. We'll try to answer that question next week. But that's something good that you brought up. Okay. Power calculations. Michael, would you like to take this one?
Yeah. So basically, these are applying the same equations as we used before. So once you've made your circuit and you know the voltages and you know the amount of current it's going to pull because you calculated the resistances using the loop equation thing, Kirchhoff's law, and all that stuff from before, you can combine it together to calculate your wattage or power. So what is power? We talked about this 2 or 3 weeks ago a little bit when we were looking over an introduction to physics. And basically, power is energy over time. So it's the amount of the ability to do work over time. It's like how much energy is flowing per second. And that's what wattage is. So 20 watts is 20 joules per second. And to calculate it, it's super simple. You multiply your voltage times your current, and that gives you your wattage. So for reference, your phone probably uses anywhere from a 5 to 15 watt charger, meaning that is being given 5 to 15 joules of energy per second. A hairdryer uses upwards of 2,000 watts. And the reason this is important is because wattage produces heat. So, for instance, you have this thing called a breaker in your wall. And if you have too many things connected to one breaker, the breaker pops. And basically, what the breaker is doing is it's detecting how much current, which is directly related to how much wattage all the different appliances that you have connected to that circuit are drawing, And if it goes above a certain threshold, it pops because if it doesn't, your house sets on fire. And we don't want your house setting on fire. So that's why we do power calculations and we have voltage breakers and we do all the math before we actually
Hello.
test it. Yes.
So one more question. So I think for the voltage or the resistance to pass through, there is something called a fuse wire also, right? That
Hmm.
controls if the voltage or power is more, it like breaks the voltage so it doesn't burn the object.
Yeah. So a fuse is the same thing as a breaker, except typically when we talk about fuses, they'll kind of like single use versus breakers, they just pop. Um, But yeah, fuses are the most basic example of breakers, and they're used in basically everything to protect circuits. The point of a fuse is to protect the circuit, and it works in the exact same way. When your circuit is pulling too much wattage, um, as you increase the amount of wattage pulled across a fuse, and they look like little glass vials, the amount of heat that is produced on that little fuse increases. And once it gets above a certain threshold, the fuse actually melts, cutting the circuit in half and saving your circuit from frying itself to death or setting fire in much the exact same way. So, good thing to bring up, Thomas.
Cool. Yeah.
Actually, I had the answers to Thomas' question, which he asked, what is quorum sensing processor? It is not actually an electrical thing that you would put in an electrical circuits. That things are for a bacteria that are living in our guts, and the quorum sense. It is called a quorum sensing process, not a processor. The quorum sensing process happens, consider it, I give you an example. If we have 3,000 bacteria, consider it in our guts. They are good bacteria, and bad bacteria are attacking them, and their population is getting less. So now we will use the strongest survives, So the stronger cells, the good bacteria cells, which are having better gene or an resistance to those bad bacteria, they will share their genes to the weaker bacteria, good bacteria, so that they can survive in our guts. This is called a quorum sensing process and not a processor, which only happens in our guts, not actually inside an electrical circuit.
Wow.
Wow,
That
that's
was
a
that was
that's
very
a
impressive.
that's an impressive biology lesson.
I feel like you should teach next class. That was very
Could
that
yes.
was very good. Thank you for
Wow.
sharing that. I hope
Yes,
that
thank you,
was
Sherman.
a good answer to your question, Thomas. So very well. And this was good having discussions as a group. If anyone has anything else to add, I know Thomas likes to add in. I'm sure he's done electrical circuits in the past, so he's very well versed in that. So that's very good. So keep adding new things. We'll keep having discussion, but that's very beneficial for us. Okay, so here are some very complex circuit diagrams. These are like very, very complex. So if we look at this one in the top right, we can see some things that we know, right? So we see things like cells, we see switches, and whatever else there might be. So again, there's all of that. So those are some pretty cool images that we are sharing.
Hmm.
Okay. So here's some further readings on electrical circuits and designs. There's a YouTube video here, and there is a article here. We will post all of this into the WhatsApp group chat. So we'll post the recording as well as this slideshow, so you guys can go back, paste this link into Google, and just basically further your understanding. And again, this is optional, right? So these readings are optional. But if you really like are interested in electrical engineering or any type of engineering, this is something that you really need to know. So highly recommend doing that.
I sent a small simulation software in chat. If you are interested, I know my physics class actually ended up using this. It's a very, very basic software. There are definitely more advanced ones out there. But if you just want to test out resistors and light bulbs and switches, and for some reason it has dollar bills in it and erasers, um, it's a cool one to check out. And basically, what it allows you to do is create very basic circuits, set some voltages, create some resistors, set the resistance, and watch in real time, well, in simulation time, as the electrons actually flow around the circuit. And if you take your little tools on the right, and tap them around on the circuit, it will actually calculate the voltage and the current flowing through the circuit using the exact same Kirchhoff's voltage and current laws that we discussed before. So it's a cool little tool if you want to try it out. Um, I just thought I'd throw that out there. Yeah, of course.
Cool. So, again, thank you guys for joining. This was our week 6 presentation regarding electrical circuits. Appreciate everyone who came and consistently shows up. We usually have the same 3, 4 faces showing up, so that's very good that you guys keep doing that. Here we have again our Instagram, our email. I think TikTok is actually banned in India, so but our
Oh, oops.
yeah, our Instagram. If you guys would like to follow us and keep a tab on what we're doing, like our robot and anything like that. But that is all from us. Thank you guys for joining, and we will see you guys next week. Have a
See you
good one,
guys.
guys. And any questions, you guys can stay back and ask. But that is all for us. And